Uranus is not only an absolute planetary maverick, but also a complete research mystery. No wonder, after all, the shimmering blue ice giant was only visited by Voyager 2 and studied up close, and accordingly the data is sparse. Despite all this, however, researchers have now succeeded in revealing a number of Uranus's characteristics that are as astonishing as they are confusing. The planet actually orbits the Sun on its side. Its magnetic field has not just two, but four poles, and its surface is a frosty 216 degrees colder than it should actually be. But now astronomers have finally managed to shed a little more light on the darkness of Uranus, and its strange four-pole magnetic field probably goes back to a remarkable spectacle hidden deep inside the celestial body the Uranus family has grown, because it was only a few months ago that experts announced that they had detected a previously unknown moon in the realms of the distant ice giant. Accordingly, the number of Uranus's companions increased from 27 to 28, and as befits a lunar baby, the newly discovered satellite is also the smallest of all Uranus's moons found to date, christened with a provisional name S223U1. It's just 8 kilometers across, but the bigger question marks that have been swirling around Uranus for many decades are all the more reason to be curious. As already mentioned, this is primarily because the most up-to-date data available to us about this bizarre ice world still dates from 1986, but although the information collected by Voyager may seem a bit outdated, it's still good for new surprises and detail. The Voyager datasets revealed a strikingly strong radiation belt full of energetic, fast-moving electrons in the planet's magnetosphere. The intensity of the particle currents was even comparable to that in the extreme magnetosphere of Jupiter, but in contrast to the king of our planetary system, there was hardly any plasma in the realms of Uranus from which the electrons could have originated. This seemed all the more puzzling given that the 5 largest Uranian moons should have been incessantly releasing water molecules into space, which would then be ionized by the magnetosphere of the ice moon. And so it was that for decades experts struggled with the Voyager data, and only now have they managed to provide an explanation for these strange conditions. In fact, the key to the astronomical breakthrough was also hidden in the old data sets, but the scientists had simply overlooked it until now. This only changed when the team led by Jamie Jean-Sky from NASA's Jet Propulsion Laboratory took another look at the data. Voyager 2 had also analyzed the radiation and particle density in space in the days before and after its flyby of Uranus. But in fact, a strong solar storm had occurred shortly before the passage. This compressed the magnetic field of Uranus and tore the surrounding plasma out into space with it. And while this event robbed the magnetosphere, the solar storm filled the planet's radiation belt with high-energy electrons. In the same breath, if you like, Voyager 2 simply caught you on the wrong foot and by no means examined it in its normal state, but in an absolutely exceptional situation. Experts say that the planet's magnetosphere would have looked completely different if the probe had arrived just a few days earlier. And yet, in a way, Voyager 2 did have amazing timing. After all, the extreme conditions at the time are likely to occur only about 4% of the time. Diamonds are raining inside Uranus. There is no question that the decoding of this almost 40-year-old plasma mystery marks an important intermediate step in Uranus research, but there is also no question that the ice giant's exotic magnetic field continues to present us with major problems. But how is a planet's magnetic field formed in the first place? Well, in the case of our earthly home, which is known to have a typical dipole magnetic field, this is created by convection currents in the liquid OU core, which act in combination with the solid iron core as a geodynamo. However, this so-called dipole field, which has two opposite poles, requires a certain minimum thickness of the convective layer. This does not appear to be the case with Uranus, and the experts' models show that a non-dipole magnetic field can be generated when the currents responsible are confined to a thin layer relatively far out. Furthermore, we know that the interior of the ice giant is composed of a solid core on the one hand and a mixture of water ice, ammonia and methane on the other, which is potentially conductive and therefore a candidate for a convective magnet dynamo. What we don't know, however, is what the lower layers of Uranus look like and what could block the currents at these planetary depths. One theory is based on the assumption that the water there assumes an exotic superionic state, which means nothing more than that the oxygen atoms of the water molecule form a solid lattice in which the hydrogen ions can move around freely. On the Other hand, there is a theory that probably corresponds to the wildest dream of every jeweler. It could actually be raining diamonds inside Uranus. The fact that the interior of the ice giant may embody a planetary diamond is again due to the pressure and temperature, which are probably sufficient to break down hydrocarbons and compress the carbon into diamond crystals in the same breath as gemstone rain. Could also explain why the planet has a multipolar magnetic field after all the diamonds. Also tear gas and ice into the depths, which ultimately causes convection currents in the mantle. Since conductive molecules are also set in motion in the process, these would also contribute to the unusual Uranian magnetic field. So far, so plausible, and yet a new series of research studies has now come to the conclusion that the magnetic field mystery actually has a complex, completely different background. In this case, we are dealing neither with the effects of superionic water nor with the consequences of the diamond rain, but with the result of non-mixable layers in the planet's interior. The solution to the magnetic field puzzle. The fact that the discussion about the magnetic field is now enriched by a third approach is thanks to Burkhard Militzer from the University of California in Berkeley. In detail, the Dre and Born scientists used some high-resolution computer simulations that reconstructed the behavior of methane, water ice, and ammonia under the conditions inside Uranus. What was special about this was the fact that thanks to an adaptive algorithm, Militzer was able to simulate the processes with atomic precision for the first time, with a surprising result. When the professor of Earth and planetary science looked at the model, the water had separated from the carbon and nitrogen, as a result several layers were created that cannot mix with each other. At the very top is a conductive layer of water and ammonia about 8,000 kilometers thick, which is probably partly liquid. This is also the area where the convective currents take place, which act as the engine of the multipolar magnetic field. Just below that, there is a similarly thick zone of nitrogen containing hydrocarbons whose hydrogen content decreases with increasing depth and pressure, ultimately resulting in several layers of these compounds that become steadily denser. According to Militzer, this circumstance prevents vertical flow, which is why these layers cannot play a significant role in the formation of Uranus's magnetic field. In other words, the hidden interior of the planet behaves like oil and water, and the bottom line is that the division into two emis layers can explain why Uranus has such an exotic magnetic field. But as is so often the case, the theory still needs to be put to the test in the course of future investigations. This could be done, for example, in the context of laboratory experiments under high pressure, or in the best case, of course, in the course of a direct on-site exploration of the sobering future of the Uranus missions. Unfortunately, the truth about space probes is that there is currently simply no program that has reached an advanced stage of development and would go beyond the status of a vague concept. One of these concepts goes by the name INUS and includes two individual probes, one of which flies to Uranus and the other onto Neptune. And if the project conceived by the ESA is actually realized, the separable probe could make its way into the gigantic expanses of space in just under 10 years. Whether and when this project will actually be realized, however, is currently still written in the stars, and with it all the answers to the Uranus questions that are still unanswered. As briefly mentioned at the beginning, the ice giant is tilted at almost 90 degrees, and its rotational axis is thus in stark contrast to those of all the other planets in the solar system. In principle, researchers assume that the celestial body was tipped on its side by a massive impact. This catastrophic event likely shaped Uranus into the enigmatic world we observe today. However, the precise nature of the collision remains a mystery. Some models suggest that the protoplanetary impactor delivered a substantial amount of material that became trapped in Uranus's outer layers, altering its heat distribution and leading to its unexpectedly low temperatures. Others propose that the impact fundamentally changed Uranus's internal structure, disrupting conventional convective currents and contributing to its unusual multipolar magnetic field. Despite these theories, scientists are still searching for definitive answers. A dedicated Uranus mission would be the key to unlocking these mysteries, offering fresh data and direct observations. NASA has proposed a flagship-class Uranus orbiter and probe, which could launch in the 2030s, arriving at the ice giant in the 2040s. This mission would carry advanced instruments to analyze the planet's atmosphere, magnetic field, and potential subsurface oceans, potentially revolutionizing our understanding of ice giants. Meanwhile, astronomers continue to analyze archival data, run high-resolution simulations, and observe Uranus using space telescopes, such as the James Webb Space Telescope, JWST. These efforts have already led to significant breakthroughs, such as the detection of new atmospheric compositions and the discovery of the faintest rings surrounding the planet. As we stand on the brink of a new era of planetary exploration, Uranus remains one of the most fascinating and least understood worlds in our solar system. Whether through future missions or cutting-edge observations, the quest to unravel the secrets of this icy maverick continues. Stay tuned to Digital Discoveries as we bring you the latest updates on space exploration and the mysteries of the universe. Subscribe now and be part of our journey into the cosmos.